Hey there, calc folks back here. Oh my lights are terrible. Let me fix that. All right. Didn't realize they were as bad as they were here. Still burning out, man. What is? Do we have to turn that down some? I think I got to turn this down some. That helps. There we go. That's what you get for being bald. I've got to worry about my lights in here. My head shines way too much, folks. All right. Let's see here. I got one last video to get out to you folks here on the application. No, got a couple more. What am I thinking? I'm thinking Calc 3. We're Calc 2 class. We still got a couple things to talk about with respect to the application of integration. Surface area is going to be one of them, and that is this video here that goes along with arc length in its calculation. So we're going to get into that in our notes today, folks. We are going to look here at the case for surface area for what we call a revolution. We're going to see a calculation very, very similar to that arc length. It's going to incorporate some very similar aspects. Right? We'll take note in its calculation and in its proof. All right? It can be somewhat of an easier calculation than the length calculation. However, it still does have its cases where they are not always so integrable. The reason why it might be a little bit of an easier calculation is because of what the integrand does involve. There is opportunity there where there isn't necessarily always in arc length. And I'll point that out when we get into the formula, what I mean by that. All right? But what we do assume here is suppose we have a curve y equals f of x over values of x in this closed interval from a to b. Very much like the setup for an arc length calculation. But we take this curve and we revolve it around the x-axis in the three-dimensional space. All right? Taking a curve along the x-axis and revolving it around the x-axis in three-dimensional space is going to perform this surface, or is going to form this surface of revolution, folks. Right? And what we're going to be interested in is finding the surface area for that lateral edge, folks, for the edge formed by that curve that's being revolved. We are not going to be looking at the surface area for the circular bases. That is not included in this calculation. The surface area for the circular bases is not included in this calculation, just the surface area formed by the curve that's being revolved around the x-axis. All right? Oh, let me click onto this, make sure I'm on the right thing here. As for finding that surface area, it does involve an integration calculation. So we're going to look at that first. Suppose y equals f of x is greater than 0, right, is a function with continuous first derivatives over the closed interval from a to b. All right? The area for the surface of revolution formed by revolving the curve y equals f of x over values of x in the interval from a to b around the x-axis, right, is given by the following calculation. Right? It is given by this calculation, s equals the interval over that interval of x from a to b, right, for what is going to be 2 pi times f of x times the square root of 1 plus the quantity f prime of x squared underneath that radical symbol, and all integrated with respect to x. You are going to take your bounds of integration will be your bounds on the integral. Function f of x is going to play a role out here as a factor in the integrand. And f prime of x is going to play a role here underneath the radical as this term being squared in our radical value. All right? And that would be the setup for the formula, those individual parts. We might consider the surface area for the surface of revolution formed when we take the square root function, 4 times the square root of x, over values of x from 0 to 2, and we revolve that around the x-axis. This is going to form a surface of revolution. All right? The function f of x in our formulation is going to be 4 square root of x. However, we're going to need the first derivative also to place into here. And now if you keep in mind 4 square root of x, that's going to bump up to the Sorry, drops. Drops to the negative 1/2 power, bring the 1/2 out in front. It'll cancel with the 4, make that 2. So it'll be 2 over the square root of x for its first derivative, following just some basic derivative rules. All right. In this case, for f of x equal to the 4 root x, f prime of x is 2 over the square root of x, following some fundamental derivative rules. And the surface area would be given by this calculation seen here, where we're just going into the above and substituting in for f of x. 4 root x, our given function, and substituting in for f prime of x, the quantity 2 over the square root of x. And one thing you do want to keep in mind is you are substituting in that entire quantity that's being squared. Both the 2 and the square root of x is going to be squared in that quantity. Excuse me. That can be simplified. Notice squaring this does produce 4 over x. So, and then combining the 2 and the 4 out in front with the 8, the pi makes 8 pi. So you are left with an integrand that looks like this, that you can start to simplify by factoring out the 1 over x from under the radical. It would factor itself out as 1 over the square root of x, cancel with the square root of x, and leave you with the square root of x plus 4, folks. Again, like I said, these kind of work out a little nicer than arc length at times because of what they include. And what they do include that opens up some opportunity is the function f of x on the outside of the radical. By having that possibility for an x on the outside of the radical, there is a potential for u substitution to work more often or for simplification to happen at times, like we see here more often. Here, when we do simplify, the radicals of x cancel in the numerator and denominator, and we are left with this integrand seen here. Where to get through that integrand, this is a rather fundamental u substitution problem. We can let u equal the quantity x plus 4. All right, now from u substitution, letting u equal x plus 4, du dx will equal 1, so du will just simply be equal to dx. Right? And we can go in here and replace the x plus 4 with u, the dx with du, and then adjust our bounds accordingly. And how we adjust our bounds is we plug in 0 for x here, and we get 0 plus 4 is lower bound of 4. Plug in 2 for x here. 2 plus 4 gives us 6 on the upper bound. So we end up with this integral from 4 to 6 for the square root of u, all integrated with respect to u. Now, u's, or the square root of u's antiderivative, that is u to the 1/2 power. That is going to bump up to 3/2, and you're going to divide by 3/2 or multiply by 2/3. Right? So it'll be 2/3 u to the 3/2 power, which will be our antiderivative, and you can see that inside the brackets here. That 2/3 is a constant multiple. We could bring that out and multiply that by the 8 pi, 16 pi over 3. But then we evaluate that u to the 3/2 across those bounds, folks. And if we evaluate across those bounds, right at 6, u to the 3/2 becomes, 6 square root of 6. And when we evaluate it at 4, that would become 4 square root of 4. Now, square root of 4 does simplify to 2. 2 times 4 is 8. So the value inside that brackets could be thought of as 6 root 6 minus 8. I do think we have some constant multiples, or we could redistribute the 16 thirds into that, and we get 32 root 6 minus 128 thirds times pi units squared in surface area. All right. Folks, that is our surface area calculation seen there. All right. Now, as for proof, following from our calculation, right, we do see that also presented here in this set of notes, right? And it begins as we did with the other proofs. We are going to take that closed interval from A to B and slice it up into n subintervals, right? Where again, we're going to let delta x be the width of the k subinterval. It's calculated by b minus a divided by n. And we're going to let x sub k represent a value of x in the k subinterval. We're going to need that, right, in our calculation. And a lot like the case for arc length, we're going to also need to take note of delta y. Delta y, again, being that change in y equal to f of x over that k subinterval. Is over that k subinterval, x is going to change by its width, and y is going to change so much graphically. Delta y is the amount of change that corresponds to this change along x, right, on the kth subinterval. We're going to let delta y be that quantity. Right? Subdividing that closed interval from a to b into n subintervals is in turn going to subdivide up our solid. Right? Not our solid, our surface. This isn't necessarily a solid now, this is a surface, and I try to highlight that in my imagery here. And it's going to slice it up into n slices, and you can see here is my solid in this illustration, and you can see there that we are just looking at the surface area, this lateral edge we say. And this is formed by taking this green curve f of x and revolving it around my x-axis, the blue straight line through my image here. All right, through my three-dimensional image. We're going to slice up that interval from a to b along that line into n subintervals, which is going to slice up this surface. And you can see those slices here respectively, right? Down here, and those slices have cross-sections that separate themselves in the shape of circles. Take note. All right? But when we think about each of those slices here approximates a shape known as a frustum. All right? The image I have highlighted there on the screen is what's known as a frustum. Essentially, it's a cone where we have taken the tip and cut it off. Right? That is just a cone whose tip has been removed. Right? There's no tip out here on the left side to this cone, but other than that, it is a conical shape to it. Without a tip, that's known as a frustum. Right? And we do have a formula for calculating the surface area of a frustum. To calculate the surface area of a frustum with a smaller radius of little r and a larger radius of big R, and a lateral surface length, given by little l here, right? The actual surface area formed by revolving that lateral length along this horizontal axis is going to be given by this calculation here. It is going to be pi times the sum of the two radiuses, little r and big R, multiplied by the length, right, that lateral length between little r and big R's circular edge on the cone. Right, this measurement here. That will give me the surface area little s for this frustum. Well, each of these cross sections in my illustration illustrate this shape as a surface. So for an approximate of that surface area, what we can do here for the case slice is we could approximate it as follows. In the case slice, we grab any one of these slices. The surface area for that slice is going to be pi times the two radius measurements added together. Now, how we're going to approximate the radius measurements is we are just going to look at the value of our function f of x at x sub k. That value of f of x at x sub k can be used to approximate both the lower and the upper radial measurements for this frustum. Right? Especially if we put x sub k right in the middle of that subinterval. It would be a good approximate f of x sub k for both the lower and the right bound. But as we increase our number of subintervals, it doesn't really matter in the end. Right? It becomes a good approximate for both bounds. Right? Both radial measurements on either end of those frustum shapes. All right? So we'll go ahead and use it as f of x sub k plus f of x sub k is big R plus little r. Again, we're just approximating here, folks. That's the key. All right? And then that is times by this quantity. We have seen this before. That is the length. That is the length of that kth section. That is the length of the green line over that kth subinterval. And we saw back in arc length that we calculated that using a little Pythagorean theorem in these measurements of delta x and delta y. Same idea here. All right? This is similar to what we saw back in arc length. Now f of x sub k plus f of x sub k is 2 times f of x sub k. And we saw back in arc length that this can be rewritten by factoring out a delta x. So all of this statement can be rewritten as this here. This becomes our approximate for the kth subinterval. Its surface area. To make that an approximate for the total, where I do point out here a little bit of what I've already noted with respect to that approximate. But as for the approximate of the total surface area, we add all that up for each and every kth subinterval. Right? We saw that in our proofs, and this is our summation there, where that approximation can be made exact by then applying a limit. And we know when we apply a limit to this, we can then apply the definition of the definite integral, where the limit of the summation becomes the process of integration. That integration is going to happen with respect to x in our calculation here, folks. Right? And we are going to be left with an integrand given by this quantity here, where the x sub k gets, the k just gets dropped and it's f of x. And the delta quantities, delta y and delta x, those changes in y, those incremental changes in y and x become differential changes in y and x, dy and dx, respectively. And then again, like in arc length, since y equals f of x, dy dx must be equal to f prime of x. And we're able to look at our surface area calculation seen here and replace the dy dx in that calculation with f prime of x. And what we yield here on the right-hand side is our formulation, folks. Right? This is proof. This is proof seen above. And you've hopefully seen that each and every one of these proofs sets itself up in a similar manner, and that is the integration process, folks. That is part of this idea of application of integration that you want to be taking away from this chapter of material, right, in our study of the application of integration. All right? But that is our video on surface area. Again, I'm trying to keep these short. I did incorporate some proofs, some calculation along with the formulation. Keep out there, keep practicing these problems. There's a lot of practice that I make available, help build those skills. But we are just about done with looking at application of integration, folks. We have some physics topics to come back and look at, and we will wrap from there. So, with that said, I will say that is it for the end, and I will catch you next time. Got a little jumpy there. See y'all next time, folks.